think about the last time you were annoyed by freezes in a video call. Those freezes are usually caused by packet losses. And our work, Grace, explores a completely new AI-driven design for loss-resilient video codecs. As we all know, real-time video plays an important role in our daily life. The use cases covers video conferencing, live streaming, cloud gaming, and interactive VR and AR. And also, the usage of the real-time video are still growing. Over the past year, there has been a 100-fold increase of video minutes received via the WebRTC stack for real-time videos. So, the goal of the real-time video streaming is to stream the video with constantly low delay and high bitrate. So here, constantly low delay means that there is no time for retransmissions. However, the practical challenge is that the packet losses are pretty hard to avoid in the wild. So recent work suggests that in the video calls, around 1.5% of the frames can lose 20 to 80% of their packets burstly within a frame. So here, I want to emphasize that loose packets here includes both packets dropping in the network and the packets arrived later than the decoding deadline. So networking researchers, we are usually attempted to think if we lower the packet loss rates, the users will then have better perceived quality. However, lowering packet loss may not always work. So let's do a quick survey here. I will show you two videos of the same content. And both of the videos are impacted by some packet losses, so there will be some distortion in the middle. And now, I wanted you to answer if one video is obviously worse than another video. So let me play the first video. And the second video. So can I have a show of hand here? Who feels like video A is much better than video B? And who feels like video B is much better than video A? And video A and video B, it's hard to tell the difference? Okay, so let me tell you this. So video A is impacted by 50% of packet loss, but video B is only impacted by 15% of packet loss. So the takeaway here is better network performance does not always translate to the user perceived quality. To explain why this happens, let me briefly talk about the existing loss resilient solutions in video streaming. So first, let's say how the receiver deals with the packet loss. This is done by error concealment, which guesses the missing piece based on the arrived data at the receiver side. So the sender will encode and send the frame without any redundancy. And for instance, if the frame has 4 packets and one of them is lost, the error concealment will attempt to fill in the gap. However, guessing the missing data is fundamentally difficult without any redundant information at the decoder side. For instance, the previous 2 videos, they're actually decoded with the state-of-the-art error concealment techniques using big neural networks, but still it has notable quality drop after loss. A complementary technique, forward error correction, aka FEC, operates from the sender side by adding some redundancy. For example, since the target size of a frame is 5 packets, FEC can send 1 parity packet and 4 content packets. And in this case, it can tolerate any loss of a single packet. However, if there are more than 1 packet being lost, the receiver will still fail to decode the frame and then cause the video to freeze. Therefore, FEC is only effective if the packet loss is lower than its redundancy rate. So to summarize the existing solutions, this graph shows the frame quality versus the packet loss rate. The x-axis is the packet loss rate per frame, and the y-axis represents quality. And as we can see, the quality of the video either decreases quickly as this blue line, or it has a sharp drop when packet loss exceeds some threshold as this red line. And even if we apply both techniques together at the same time, it won't be better than the maximum of both lines. So how should we improve the loss resilience so that it can achieve something like this green line? What's really missing here? The key observation is the video sender and receiver, they are often jointly optimized for compression efficiency. However, the loss resilience is rarely jointly optimized on both sides. And this leads to our key insight. Jointly optimizing the encoder and decoder on the different packet losses, it can considerably improve the loss resilience. Specifically, Grace achieved better loss resilience by jointly training the neuron encoder and decoder under a range of simulated packet losses. So to expand a little bit, there are three major design questions. First is how to train a neuron video codec. Second is how to simulate packet loss during training. And third is how to choose the loss rates during training. To explain our design, let me first briefly talk about the video codecs and neuron video codecs. So the traditional video codec takes in the video and transforms it to the code by a few steps. And the decoder then reconstructs the video after receiving the code. And for simplicity, we omitted the entropy coding step in the middle because entropy coding does not change the code. And neural video codecs, they're basically functionally the same as traditional video codecs, but just replacing the modules with neural networks. And the encoder and decoder can be seen as trainable functions, f-phi and g theta here, and the code becomes tensors. Specifically, Grace employs the neural network architecture from DVC, which is a popular neural video codec published in CVPR 19. And now, let's look at the first question, how to train a neural video codec. The training objective function can be formulated like this. The first factor is the pixel level deviation calculated by the MSE between the original video x and the decoded video x hat. And the second factor is the size of the coded tensor y after entropy coding. So the size function here is a differentiable function that approximates the entropy of y. By minimizing this training objective, we can actually train a pretty good neural video codec with similar compression efficiency as traditional codecs like H265. So the next question is how to simulate packet loss during training. First, we introduce a function called p-loss. This is to simulate the packet loss. After applying p-loss, we got the coded tensor after loss, which is denoted as z. Then, instead of g theta y, the decoded video becomes g theta z. And therefore, we simulate the packet loss by just slightly changing how to get the decoded video without changing the main part of the training objective functions. Okay, practically, it's critical that the packet loss during inference should mimic the p-loss during training. In Grace, both p-loss and actual packet loss randomly zero out the elements. So during training, p-loss multiplies the random 0-1 mask to the coded tensor. And for inferencing, Grace first randomly divides the coded tensor into multiple partitions. And this partition are then sent as separate packets over the network. And the Grace decoder reassembles these partitions back to the original tensor. So in this case, if a partition is lost, its values will be zeroed out without impacting other partitions. And thus, the impact of packet loss during inferencing mirrors that during training, i.e. the random zeroing of the elements. And so far, we already know how to involve the packet loss during training. The remaining design challenge is selecting the appropriate loss rates. So initially, we had no loss during training. And the observation indicates that the frame quality declines quickly when packet loss increases, as depicted in the right figure here. And next, the design choice is to distribute the loss rates from 0 to 100%. And then we got this blue curve here, which has better quality when the loss rate is high, but worse quality when the loss rate is 0. Since in the real world, the most common case is there is no loss. This blue curve is still not ideal. And in Grace, our design is we adding more zero loss during training and also increase the ratio of seeing loss between 0 and 60%. And this gives us a green curve here, which has better quality than the red curve at low loss, and also still decent quality at high loss. In the paper, we also tackled more issues to make Grace practical, such as how to do the real-time encoding decoding on both GPU and mobile devices, how to quickly adapt bit rates, and how to minimize the error propagation caused by packet losses. Please refer to our paper for more details. And we did a bunch of tests to evaluate the performance of Grace. First, we made a testing set of 61 videos from 4 public datasets, which are totally different from the training set. And it covers multiple different scenarios. We use the average SSIM in dB as a quality metric, and there are 3 major baselines. The first one is WebRTC using H265 and FEC. We use the latest FEC technique called Tumblr from last year's NSDI. And the second baseline is error concealment. We use a recent flow-guided neural network-based technique from CV community, which is published in ECCV 2022. And the third baseline is scalable video coding with FEC at the base layer. We also have multiple other baselines in our paper, so please refer to the paper for more details. And the first thing to verify is, does GRIS really have better loss resiliency compared to those baselines? So here, the x-axis of the figure is the frame level packet loss, and the y-axis is the quality of the frame. Just in case you forgot, the packet loss per frame here includes both packets dropped by the network and the packets received later than the decoding deadline. So the SVC and error concealment, those quality will decrease quickly when the packet loss rate increases. And the FEC-based methods have a sharp drop in the frame quality if the loss rate exceeds the redundancy rate. Also, it sacrifices the quality at zero loss for more redundancy. And in contrast, GRIS has a more graceful quality degradation when the packet loss increases. And it has better quality on all the packet loss rates than all the other loss resilience schemes. So how does the frame really look like when there are packet losses? Here, we show the visualization of the decoding image by GRIS and error concealment. We apply 50% of loss rate to 3 consecutive frames from the kinetics dataset. And in the original frame, the woman holds a Q stick. And in the frame decoded by error concealment, the Q stick is distorted and blurred. GRIS can recover the image with much less blurry and distortion, and also have higher SIM than error concealment baseline. So you may wonder whether the GRIS loss resilience feature is because the neural encoder sacrifices the compression efficiency to get more redundancy. This figure shows the comparison of compression efficiency across all the 720p videos in our dataset. The x-axis is the video bitrate, and the y-axis is SSIN. The yellow curve here is H264, and the blue curve here is H265. Both of them are using the very fast encoding mode. Although it does not represent the optimal performance of traditional codecs, the very fast mode is also widely used for real-time videos. And the GRIS is a green curve here. So overall, when there are no packet loss, GRIS compression efficiency is better than H264 and comparable to H265. So it does not sacrifice much compression efficiency for the loss resilience. And finally, we test the video quality versus smoothness trade-off of GRIS on the real network conditions. So we conducted an end-to-end video streaming experiment based on WebRTC framework where the bandwidth fluctuates between 0.2 to 10 Mbps. And in the figure, the x-axis is the ratio of time that the video is freezing, and the y-axis is the average video quality in SN. So although the error concealment is here, although it does not have much video stalls, it suffers from low quality after packet loss happens. And SVC has better video quality, but also more video stalls because it needs to wait for the retransmission if the base layer is damaged. And WebRTC has higher video stalls even with FEC. This is because it cannot accurately predict the future packet losses when bandwidth changes, and needs to freeze the video and wait for retransmission more frequently. We also had another baseline called Salsify from previous year's NSDI. It can stream the video at a pretty high bitrate and skip some frames when the packet loss happens. And as a result, it has a pretty good quality, but slightly higher stall ratio due to frame skipping. In contrast, GRIS keeps smoother playback without video stalls and only a negligible quality drop compared to WebRTC. So what does this trade-off mean in the real world? So one is high quality but minor glitches like WebRTC and Salsify, and another is smooth playback but a little bit of quality drop like GRIS. To answer this question, there are 2 demo videos streamed by WebRTC and GRIS on the fluctuating bandwidth. So let me play the first video here, streamed by WebRTC. And as we can see, the video it has actually multiple glitches during the playback. And in contrast, let's look at the video played by GRIS. It's actually much more smoother with not notable freezes. So to check what kind of videos are more favored by users, we conducted a user study. We randomly sampled 8 videos covering different scenarios and streamed it using GRIS and other baselines. And then we collected almost 1,000 user ratings from 240 amateur workers. The result shows that GRIS can increase the mean user rating by more than 30% compared to other baselines. So the takeaway here is most users favor GRIS, i.e. the smoother playback, over the smooth quality with some glitches. To conclude, in real-time video streaming, the objective is to stream high-quality, low-latency video under unpredictable network conditions. To achieve that goal, our insight is we can improve the loss resiliency by jointly training the neural video encoder and decoder on the simulated packet losses. And we build Grace based on such insight. When the packet loss happens, Grace can still stream video without freezing or significant quality drop, which is more favored by users. And we also make the source code, models, and the datasets of Grace public. So please visit our website for more details. And that's all of my talk. Thank you.